appreciate it. I don't think I'll ever learn my lesson. Okay, we are recording Chem 8, Monday, Wednesday, Friday, fall 29/28. Okay, so we are talking about hybridization and why hybridization happens. Hybridization happens to prove a point. Hybridization happens to help us explain why methane has 4 identical bonds. So methane, I'm going to start with methane this way. Okay? Does it focus properly? Carbon. On the whiteboard.
Ahí se oye que ya están, ¿no?
No, le digo que si ya las buscó, dice que no sabe.
Ya están.
Hold on. Why am I having? There you go. Okay, I'm muting everyone. If there was that's fine, no problem. Don't feel bad. Okay, this is the 3D representation of methane molecule. Okay, and 4 hydrogens. Okay, this is dead. Uh-oh, I don't have any more blue pens. That's fine. We'll have to do with purple. 4 hydrogens. Okay, and the molecule essentially looks like this, just to give you a reminder. Okay, 2 bonds, the one that's going up north, that's on the whiteboard. The one that's southwest, that's on the whiteboard. The one that's coming toward this direction, this guy, this is out, that's the wedge. And the one that's behind the whiteboard, that's with the dash line, right? Okay, I'm not going to spend a lot of time. And this carbon, because all the bonds are identical length and all the angles are the same angle, okay, 109.5 degrees, and this arrangement is called tetrahedral. Tetrahedral arrangement, which I showed you in the cube. So the consensus is that carbon in the ground state looks like this: 1s2, 2s2, okay. Looks like this. That doesn't do the job. So it must go to carbon excited state where 2s bumps 1 electron to 2p. And now we have 4 electrons in the outermost shell, shell number 2. So carbon starts to look like this, but they kind of looks like this. Okay, one orbital is kind of short, with 3 orbitals are kind of long. So in that case, that would lead to a wrong perception of methane's size. Okay, and something else happens. sp3 hybridization happens now. sp3 hybridization happens, and then carbon is in sp3 hybridization state. And what does that mean? Well, these 4 orbitals are now identical orbitals, not high or low energy, and each is called sp3. Why 3? Because there are 3 p orbitals, 1, 2, 3. Why just s? Because there is one s orbital. S1, 3p, p3, but then we don't put that 1 after s, okay? And each hybrid orbital has 1 electron because you started out with 4 electrons, you end up with 4 electrons in 4 identical orbitals. Then this guy hangs out with 4 hydrogens, each providing with a 1s electron. And when that happens, then you get the molecule. In CH4, it's the CH bond. Each is a CH bond. And you have 1 electron from, you know what, let me just change the color of it. 4 hydrogens, each coming with a 1s orbital electron, not orbital. So these are the 4 hydrogen electrons, and this is a CH bond. Each covalent bond has 2 electrons. 1 electron from carbon, 1 electron from hydrogen. Okay, so let's change the color maybe. Okay, let's make this guy, because of my blue pen concern, let's change them to red color today. For today, hydrogen is going to be red, whether you like it or not. Okay, so that's the deal. Okay, so this electron, this electron, this electron, and this electron, they're the 4 hybrid orbital electrons. Each is an sp3 orbital. And this electron, this electron, this electron, and this electron, they're coming from 4 hydrogens, they're all 1s. So if I ask you, we have gone through it once in the past, it could be a test question. What's the makeup of each CH bond? If I ask you, what is it made out of? Made out of what? Then you are supposed to say carbon's sp3 orbital and hydrogen's 1s orbital. Or you can just say something like sp3 and 1s, something like that. 1 electron from sp3 and 1 electron from 1s. That's how each of these bonds are made. Just take a look at it for maybe 15 seconds and make sure you're okay with what we have seen. This is review. This is just review. I'm going to go to a different molecule after this. We're going to introduce 2 other hybridizations, but before we do that, let's expand sp3 a little bit beyond carbon. Okay, so I'll try to keep my mouth shut for like 15 seconds. Any question is welcome. Okay, I think 15 seconds are over. Okay, all right, so this is what happens in CH4. Okay, so this is what happens in CH4. This is the carbon-hydrogen world. We're going to be spending a lot of time with carbon and hydrogen in different kinds of alkanes, like molecules bigger than methane, and alkenes when you have double bond. I'm planning to cover it today, but we'll see how far we go. And then we'll talk about alkynes where you have a triple bond. Okay, so this is CH4. We have already seen a few other molecules at the beginning of this class. We talked about this sort of molecules. Like what happens when you make a molecule with nitrogen and hydrogen? Let's keep hydrogen red today. Okay, nitrogen and hydrogen, and oxygen and hydrogen. Okay, and it turns out, let's divide this area and let's talk about them separately. Okay, nitrogen's electronic configuration goes like this. Let's just do level 2. We don't care about level 1. Core shell, I don't care anymore. Okay, we don't care anymore. 2s and 2p. Okay, hydrogen is pretty much the same. Hydrogen is providing with 1s. Okay, oxygen, on the other hand, is going to be 2s (2s, 2p), and hydrogen is going to be the same, 1s. Right? This is just review, old material, right? Electronic configuration. I'm not writing 1s, so don't get confused. Like, okay, let's check where you are if you're on top of your materials. Don't cheat. Don't look on in the internet or in the book. What's the atomic number of nitrogen? Unmute and answer. What is the atomic number of nitrogen?
7.
Sorry, Trevor?
7.
7, but it looks like 5. Why 7?
Because that's just the valence electrons.
That's just the valence electrons. Yes, Louis, that's right. Yeah. So don't fall in that trap. If I do show you that and ask you what's the atomic number, or if I say, let's see if I have a really twisted side of my, moment of my brain at that point, I say, what's the number of protons that nitrogen has? 7, not 5. Okay. What's the atomic? How many protons does oxygen have? How many protons does oxygen have? Anybody?
8.
8, not 6. Good. Okay. Now, when we did this, and when we did Lewis dot structure, life was easy. Life was not that complicated. All we did was this. And we said, 4 quadrants. Each quadrant has to have some electrons. We cannot put the electrons like this. This is just ridiculous. This is not right. That's not how it happens, because it can only use the electrons in 4 different corners. So that's wrong. This is right. So if this is right, then the molecule with hydrogen will look like this, because the lone pair cannot be used to make a bond, because each bond requires 2 electrons, 1 and 2. Any shared bond is making use of 2 electrons, one from this side, one from that side, okay? Or up and down, whatever orientation the molecule is in. So the bottom line is nitrogen can couple with 3 hydrogens and make a molecule NH3. Okay. Similarly, oxygen, what we learned at that point, before we learned hybridization, oxygen would be looking like this, and it only has 2 like single anchors or tentacles to bind with 2 other species. Like if this is an octopus, it can only pick up like 2 crabs. Okay, I don't think it happens in real life, but you get the point, hopefully. So this is the formula of the smallest molecule made from oxygen and hydrogen. So it's going to be OH2. Okay. Now, the question now is, does it just do the bonding from 2s orbital and 2p orbital? Does it mean that this is 2s and this is 2px, this is 2py, and this is 2pz orbital, and this is 2s and this is 2px, and this is 2py, and this is 2pz? Is that how it happens? In real life, it turns out that's not how it happens. This is a question. I'm just going to put a question mark here. Is this how it happens? No, it doesn't happen that way, because, again, it has been found that the lone pairs are not different. If that were the case, the two lone pairs would have two different types of properties. It's still in focus. Would have two different types of properties. One lone pair would be small, another lone pair would be big, right? But that's not the case. Both are identical. Both are identical. So scientists scratch their head a little bit more, and then they say, well, you know, even though it looks like it's all set to make a molecule, it still undergoes hybridization. What kind of hybridization? It mixes 2 electrons in 2s and 3 electrons in 2p, and they do the same type of hybridization, sp3, and they make 4 almost identical sp3 orbitals. Okay, there is not much to talk about here. sp3 orbitals. This is a pair, lone pair. This is single, and this is single. And in the real molecule, when it makes NH3, when it makes NH3, it looks like this. And a hydrogen, H3, NH, 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 and each is an NH bond. In NH3, if this is nitrogen, leave that alone. Don't mess with it. That's how NH3 looks like. The nitrogen does undergo sp3 hybridization because the data and the results and the evidence kind of lead to that direction. Same deal happens here in water. Oxygen undergoes sp3 hybridization and produces 4 sp3 orbitals. Two are lone pairs, untouchable. 2 are lone pairs and 2 are single electrons. And then in water, when water happens, this is what it looks like. 4, they're not orbitals anymore, they're OH bonds, right? So this is a lone pair. This is a lone pair. So lone pair, lone pair. Lone pairs can also do mischief, but we will talk about that a little bit later. And these two are oxygen hydrogen bonds in our famous water molecule. Okay, so that's how it looks like, and the molecule will look like this. Two lone pairs like 2 bunny ears. If you want me to kind of make it look like a cartoon. Okay, this is how water looks like. Okay, now when we talk about their shape, well, let's take a 15-second break again. Make sure that you guys are okay with what we have learned so far. I'll keep my mouth shut for 15 seconds. Carbon, ground state, excited state, hybridized state, molecule state. The excited state doesn't have to happen for nitrogen or oxygen because you don't have to unpair, unstick anything. Just the ground state, not enough. Hybridization, The hybridization state looks a little different because in carbon, they're all single. Over here, there is a pair because nitrogen has an extra electron in the second level. That's why. Oxygen has 2 lone pairs because oxygen is born that way. It has 1 extra proton and it has 1 extra electron. That's why. So the number of valencies drop as you're going that way, right? Carbon was 4, nitrogen is 3, oxygen is 2, fluorine is 1 because fluorine has 3 lone pairs. We haven't covered that yet. I was going to ask you to kind of practice that before you come back on Wednesday. And then in NH3, this is what it looks like. It kind of looks like CH4. It's similar to CH4. The only difference is this is sort of Lewis dot structure. So this is CH4, that's NH3, and that's water. Okay? It's different molecules made from hydrogen and other elements that make covalent bonds. CH4, NH3, and OH2. And this is how it happens. Any questions so far? Are we doing good? Okay. So CH4 looks like a perfect tetrahedral. Okay. NH3, I don't know if I have green bonds. I think I do. 1, 2, and 3. So if I try to make an NH3 molecule here, okay, I don't know how am I going to explain that this is a lone pair. Let me see if I have any funny looking shape. I'm going to stick it to the central thing that's green. Okay, so think about NH3. If this is CH4, yeah, you can see it on the screen. If this is NH3, okay, and that's a lone pair, think about it as a lone pair. I mean, how do I show the lone pair? My wife stole all my model set. That's okay. Okay, all right. So this is like a tripod, okay? And there is a lone pair. So it's kind of like a tetrahedral shape. How would you describe this shape? This is a perfect tetrahedral. Okay, this is perfect tetrahedron. This is a perfect tetrahedron because there's no flaw in it. This tetrahedron is a perfect tetrahedron, no matter how you look at it, okay? All the bonds are perfectly, all the bond angles are perfectly 109.5. This guy is not a perfect tetrahedron because it's got a lone pair. So 3 identical things, 1 something that's different. Please mute yourself, maybe. Okay. How would you describe this shape? Anybody has any idea? You can call it something tetrahedral. How would you call it? What adjective would you use before tetrahedron? If tetrahedron is a noun, how do you describe the tetrahedron? Don't call it screwed up tetrahedron. I like to use that word too often. My wife gets upset. How would you describe it? Any idea? What does it look like? I'll try to use the right color, the closest color, maybe brown. In the land of sand, what am I hinting? What are these called?
Pyramidal.
Pyramidal. You can have also a pyramid that looks like this. This pyramid is 3, like a triangle at the bottom. You can also have a pyramid that looks like this. So if it is this and not that, how would you call it? What kind of pyramid? One, di, tri, tetra. So you would call it something with tri. Trigonal pyramid. Good job. This is called trigonal pyramidal. Trigonal pyramidal. If you cannot remember that, let's say I asked you, it's a free response question, it's not going to happen. If I write that, if you're having a blackout and you can't remember that, all you remember is tetrahedral, but you know it's not a tetrahedral. How would you get by there? How would you survive? What's the street? How are you going to use your street smartness? How would you call it? What kind of tetrahedral? No idea? Anybody? Just use a word that you know. It's not a bus. It looks like a bus, but not exactly a bus. It's called distorted tetrahedral or trigonal pyramidal. Okay, if I ever ask you when in 128A or B, maybe we'll be a little more careful about what we say, but you know, in this case, since you guys are not going to be using chemistry so much down the road, so if we teach you something little sketchy, then I think it's okay. I will still have my job. If I ask you what are these angles, you can say roughly that sign, the alternating current sign, that means approximately. You can say approximately 109.5 degrees. Got it? Distorted tetrahedral, because it's not a perfect tetrahedral. It doesn't have all identical bonds. It's sort of tetrahedral, and it's got, the angle is not going to be perfectly tetrahedral because the repulsion between the NH bonds and the repulsion between the lone pair and the NH bond will be different. So it'll probably close up or open up a little bit, okay? You can Google the angle of HNH bond in NH3. You can figure out what that bond length is, okay? You can say, for the sake of exam, for this course, you can say approximately 109.5 degrees, okay? So that's that. For water, where is my purple bond? I have to use this, unfortunately. Okay, for water, the purple bond, I'm just using it. Think about, because it's an oxygen, I don't have a purple tetrahedral connector in the middle. Okay, let's say this is water. Okay, if you take into consideration that there are 2 lone pairs, that's a lone pair, bunny ear, that's a lone pair. It's small in the model, but in reality, it's bigger than that, right? Lone pair is not as big as an OH bond or NH bond or CH bond, but it's pretty big. So they're probably bigger, right? So this is how it looks like. So if you are not being creative because you're too tired before the next exam, you had a sleepless night, you kind of freaked out, all you can remember is tetrahedral, but you know that it's not a tetrahedron. How would you call it? What would you call if you cannot think about anything more creative? What tetrahedral? Read what's written there. Speak up.
Distorted.
Distorted what? Distorted mind?
Tetrahedral.
Distorted tetrahedral. So you can call it, I'm just going to abbreviate it. DIST, distorted tetrahedral. Okay. If you want to be creative, what does it look like? An English alphabet. Say what you see.
A V?
It's a V. You can say V-shaped, or you can say it's not straight. It's what?
Bent.
Bent. There you go. You can call it distorted tetrahedral or V-shaped, or you can call it bent. It's that simple. See, organic chemistry is really, really like meaningless stuff. You can do it. It's not that difficult. So I think I'm going to erase the board. But before we get there, methane, CH4, carbon is tetravalent. 4 electrons in level 2. 1s, core electron doesn't matter. No lone pair. Carbon has no lone pair. And this bond is made out of sp3 and 1s. sp3 and 1s. sp3 and 1s, same is true there. Okay, that's CH4. This is ammonia, NH3. 1 lone pair, NH bond. Shape tetrahedral, not exactly distorted tetrahedral. Or if you don't remember the word distorted, you can say almost tetrahedral or imperfect tetrahedral. Just use some word that makes sense. I'll give you points if there is a free response question. Bond angle approximately 109.5. It's not perfect. If you want to say something else about the shape, you can say like a pyramid, but you need to specify what kind of pyramid. Trigonal pyramid, 1, 2, 3, 3 points on the base, like a tripod. Water, bent, V, distorted tetrahedral, bond angle, approximately 109.5. It's not, it's down, it's like 104, okay? So these are the 3 compounds that we talked about, okay? I'm going to take a snapshot of the board. I'll wait for like a minute. 8:33, we have like 10 minutes left now. I want to talk about something else. Go through the board, just make sure you're comfortable what's going on the board. Different types of molecules, but similar guidelines, same type of hybridization. They're all going through sp3 hybridization. Okay. You need to retain all this knowledge. So you need to watch the videos. You need to look at the pictures. If you're more comfortable reading from the book, then do that. Okay. Looking good. It's going in there. Okay. So let's erase the board and let's talk about a different kind of a molecule. Okay, I don't think I'm missing out anything. So we'll talk about electronegativity maybe a little bit later. We have kind of covered it, but let's get back to that maybe on Wednesday. But before we get there, let's talk about a different kind of hybridization. Okay, so one of the bottom lines is that if you see a molecule, and if I ask you what kind of hybridization is there, how would you answer that question without getting too worked up? Okay, You need to stay calm and cool and still give me the right answer so that you do well in the exams. So that's the whole point. So if you come across a problem like this, let me just wipe the board with, I do have some kind of type A personality disorder. Okay, so if you see a molecule that looks like this, I definitely need new pens by now. Okay. So this is CH4. This is CH3, CH3. This is CH3, CH2, CH2. I'm just going to extend it. CH2, CH3. This is NH3. This is CH3, NH2. This is CH3, CH2, OH. Okay. If I ask you, what's the hybridization here? What's the hybridization here? What's the hybridization here? What's the hybridization here? Here, 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 here. If I might try to trick you, I might say, what's the hybridization here? What's the hybridization here, here, here? How do you answer the questions, okay? Pretty straightforward. There's nothing, it's very simple. More you think, more you will get convoluted, and you're going to be more likely to screw up. What does it look like? Let's break it down. That's how this guy looks like. What does it look like? Well, it looks like this. It's the next alkane. It looks like this. Okay. This guy, how many? 1, 2, 3, 4, 5. NH3. Lone pair, don't forget. You don't really have to draw it here because I didn't ask you to draw a Lewis dot structure. I said hybridization. You're trying to figure out the answer. CH3, CH2, OH, right? So let's erase all these arrows because they might be a little disturbing, might prevent you from concentrating on the molecule itself. Let's forget about the question. Okay. So if I ask you, what's the hybridization here? What would be your answer? We already covered it. What's the hybridization here? Speak up. We just covered it.
sp3.
Thank you. We just covered it. What's the hybridization there? If you cannot answer that, I'm going to call it a day.
sp3.
Thank you. Okay, so now if I just ask you, what do you think is going on here and here? What kind of hybridizations are there? No, it's not a trick question. It's as simple. You just take the knowledge and answer 1 dog, 2 dogs, 3 dogs. They're in a chain. They're hanging out. There's a pack, but they all have the same properties and makeup. Okay. Is there a hybridization necessary for this carbon to make 4 bonds? Yes or no? Is this carbon number 2, is it necessary for it to do hybridization? Yes or no? If yes, then what kind of hybridization will be there? Answer quickly. It's not a trick question. Wake up. I'm not
Still
looking
SP3?
SP3. What about here?
SP3.
So they're all SP3s. What about this guy here? It's not a trick question. Just take your knowledge and apply it. You learned something, you learned what is a screwdriver, what's a screw, flathead screw, Phillips screw. You're supposed to unscrew something. There are 3 screws instead of 2, and 1 screw looks different than the other screw. That's it. It's that simple. What's that? Is this nitrogen in hybridization? Is its makeup pretty much the same? Is it like this? If that's how this nitrogen looks like, okay, then in order to make 3 bonds, it needs to do something. What's that something called? It has 3 covalent bonds. 1 to hydrogen, another 1 to hydrogen, the third one to carbon, and it's got a lone pair, right? So it's doing the same thing that this nitrogen is doing in ammonia. So they're pretty much executing their same kind of ability and force. There's nothing different between that nitrogen and this nitrogen. This is NH3 and this is CH3, NH2. But essentially, the nitrogen is making 3 bonds and it's wearing a lone pair, right? Same thing here. The oxygen, unlike water, where it's bonded to 2 hydrogens, has 2 covalent bonds and 2 lone pairs. This dude is making a bond with that hydrogen and a carbon, that's the difference. And it's also wearing 2 bunny ears, the 2 lone pairs. So it's the same deal. So if it is the same deal, the mechanism by which it's doing that business should be the same, right? So what's going on here? No gesture, no chat writing, because I don't even have the chat open. What is that nitrogen hybridized? If it is yes, then what kind of hybridization is there?
SP3.
Thank you. I want to hear it from you. I'm not going to say it, because if I keep saying it, then you guys don't learn. Every time you utter the word, you are doing yourself some favor. What's the hybridization here? We just covered it. You're supposed to retain some of the information. If it is like coming in and going out like a holy tank, sounds very holy. What's the hybridization on oxygen in water?
3.
Sorry, I couldn't hear you.
SP3.
SP3. If that's the case, then what's the hybridization here in our favorite alcohol, ethanol? What's the hybridization on that oxygen?
SP3.
Thank you. So we will end today's lecture by saying this. I'm going to cut this lecture a little bit earlier. I have gone over in the past, so I'll give you a little deal today. Any element, okay? Any element, when it has multiple bonds, more than 1 bond, okay? Greater than, you know what, maybe this is not the right color. It has to be greater than 1 bond, covalent bond, okay? Not just something like this. This may not be the case. Maybe greater than equal to 1 bond. Sometimes when it's 1 bond, then it may not be a question of hybridization. Usually when there is only single bond around that element, single, they're all single bonds. When they're all single bonds, you can keep your eyes closed and you can say sp3 hybridization. sp3 hybridization. We will learn sp2 and sp hybridization on Wednesday, and we will also get into the world of double bonded species and triple bonded species. I think this is it for today. Enough. I think not 5 minutes ahead. Yeah, it's 8:45. So thank you, and we'll see you guys on Wednesday. Take care, guys. Have a good day. Let me know if you have any questions. I will have office hours. I was going to say orange hours. I'll have office hours with you guys anytime we can figure it out convenient in a moment. Okay, take care. I'll post the video and the picture as soon as I can.